Hi guys, today we're going to be talking about Chapter 7, Lecture 17, Learning Objectives 1 and 2. We're going to be looking at periodicity and our Z-effective or effective nuclear charge. So periodicity is the repetitive pattern of a property for elements arranged by their atomic number or by, in the periodic table. And many of the properties that our elements have will have periodicity about them. So it makes the periodic table so amazing, is just how well it's arranged. Properties can be predicted just based on where they are within the periodic table. Okay, so there are many properties that we're going to be looking at in today's, or in Chapter 7, that have periodicity about them. And these are going to include atomic and ionic sizes, or ionization energy, the energy to remove an electron from an atom, electron affinity. This is going to be the energy absorbed or released when an electron is added to an atom, electronegativity, the propensity for an atom of a bond to pull electron density towards itself. And then we're going to look at, probably the most important, our effective nuclear charge, which kind of it tells us all about the rest of them. So we can base all of our periodicity on effective nuclear charge in a lot of ways. And then lastly, trends within groups themselves. So groups, our columns within our periodic table, are going to have similar properties. These have properties, they have the same number of valence electrons. So let's real quick look at our first properties, and then we'll go into effective nuclear charge. So when we talk about our atomic and ionic radius, well, let's actually just look at atomic radii. It's going to increase as we go down the periodic table. And it's going to decrease as we go to the right. So across the periodic table, from left to right. Next, we have ionization energy. And it's going to have a very similar trend to our sorry, I'm trying to our atomic sizes. So our ionization energy itself generally increases as we go to the right, and it's going to decrease as we go down a group. Okay. Our next one, electron affinity, doesn't really have a significant trend. We're going to actually look at groups with this. But in general, our nonmetals are going to have a greater electron affinity than our metals. So nonmetals have a greater negative electron affinity than metals. So you actually, unlike ionization energy, where it requires energy, a lot of times electron affinity will release energy as you add those electrons in. And then next is our electronegativity. So this is, again, how much an atom of a bond pulls electron density towards itself. And it's going to increase as we go to the right, and it's going to decrease as we go down. So if we look at our periodic table, make a little periodic table here. I'm going to color code this. So atomic radius, or radii, is going to increase as we go down, increase as we go to the left. So it increases in this direction. Next is our ionization energy. Our ionization energy is going to increase as we go kind of the opposite direction, right? So it's going to increase in this direction. So as we go up the periodic table or to the right. Then we have our electron affinity. Not really going to put anything in there. And our electronegativity. So going to follow the same trend as our sorry, as our ionization energy, but note, most noble gases do not have an electron affinity. Or electronegativity. Value. Okay. And the last one I want to talk about is our Z effective. So our effective nuclear charge. The effective nuclear charge is basically talking about how much pull an electron feels from the nucleus. And all of these above trends we actually get from our effective nuclear charge. Okay, so effective nuclear charge basically talks about the attraction between the nucleus and the valence electrons. Or just electrons in general. So the greater the effective nuclear charge, the greater the attractive force that the electrons feel. I'm just going to do effective nuclear charge is Z subscript F, EFF. So the greater our Z effective, the more the nucleus pulls the electrons of the atom in. And almost always we are talking about valence electrons. So generally we're talking about how affected the valence electrons are by the nucleus or by the charge of the nucleus. Our core electrons, they don't do much. It is our valence electrons that are interacting with other atoms. They're the ones that really kind of tell us about the reactivity of an atom. So our valence electrons are the superstar of the atom. They're the things that are doing stuff. So how much they're attracted to the nucleus has a lot to do with the properties that that atom has. So the properties of the atom greatly depend on how tightly the nucleus pulls on the valence electrons. Or not pulls, how tightly the nucleus holds on to the valence electrons. So if the nucleus is holding on real tight to those electrons, they are much harder to remove. So tightly bound electrons are harder to move. I mean, as such, so a lot of times they're going to be less reactive. They're not going to do as much. Okay? And we can't just look at our periodic table like, oh, obviously this is what the effective nuclear charge is, because we have to take into account a lot of things. So if we're looking at our valence electrons, it's not just valence electrons interacting with our nucleus. We have our valence electrons interacting with our nucleus, but in between there, we've got other electrons that are going to shield the nucleus. So our core electrons shield the nuclear charge from the valence electrons, which is why it's called an effective nuclear charge, not just a nuclear charge. So the greater the number of electrons in the way, the smaller the effective nuclear charge. course, the greater the number of protons, the greater the effective nuclear charge. So you can kind of think about the electrons in between the valence electrons and the nucleus, those core electrons. You can kind of think of them like a light cover. So they're going to be shielding the electrons from the luminescence of that nucleus. So we call this shielding the screening of the electrons. So when electrons shield the nucleus, or shield the nuclear charge, this is called shielding. Or sorry, this is called screening. And what we try and do is try and calculate out our effective nuclear charge. Okay, so we have methods of calculating the effective nuclear charge. Because the effective nuclear charge, how much those electrons are being pulled in by the nucleus, they're going to have a significant impact on those properties of the atom, so it's good to know what's going on. So just as a note, as we get closer and closer to the nucleus, we're going to have a greater, or those electrons are going to have a greater shielding effect. So electrons closer to the nucleus will shield or screen the nuclear charge greater than those further away. So if you think about it in terms of our probability densities, we have our distance from our nucleus, I guess I should really distance from nucleus in angstroms, and we can look at the radial electron density. And things like our 1s orbital is very close, so they're going to shield greater than our 2s orbital or our 2p orbital. So the closer we are to our nucleus, the greater shielding we're going to have. So the very simplest way of calculating a effective nuclear charge is by saying, okay, our Z effective is equal to our Z, which is our atomic number, minus our S, which is the screening constant. Which are, in a simple form, just going to be the inner shell electrons. However, that is not a great way of determining it because, as we see from up here, different types of electrons are going to shield greater than other types. So this is where the Slater's rules were developed. So it's going to take into account that those electrons that are close to the nucleus are going to screen the nuclear charge greater than other ones. So we still have this equation, but this is now going to be calculated using rules. So our rules for Slater's rules is if we have an electron that has the same n value as the electron in question, so whatever electron we are probing information for, generally we are talking about the outer shell electrons, right? We're going to do these calculations for outer shell electrons. So this is going to be the greatest n value electrons. In this case, our S is going to be equal to 0.35 for each of those electrons. As a note, you do not count the electron that you are looking at. So if we want to know the effective nuclear charge of a particular electron, don't include it in the screening constant. Okay, now as we get close to the nucleus, we're going to have greater screening effects. So any electron that has an n value 1 less than the electron in question will have a screening constant of 0.85. And again, it's going to be for each electron. And then all other core electrons will have a screening constant of what? Okay. And what we find is that Z effective calculated for this is very good at kind of um, determining what the charge would be. So if we look at our effective nuclear charge versus our atomic number, for the first 20 elements in the periodic table, or actually for the first 18 elements in the periodic table, we see something that looks like this. Where it goes, shoop, shoop, or, shoop, shoop. There we go, something like that. Where this is number 10 and 11. And using Slater's rules, we get pretty close to that. It is a little bit low here, and even more here, and then kind of goes back.
So the pink one, advanced techniques, lots of computer calculations were done in order to get those values. But our Slater's rules does actually a pretty good job while just using the core equals 1, kind of get a weird, or S equals 1 for all core. It's not a very good approximation. Okay, so that's everything for this video. I will see you guys in the next one. Oh, you know what? Actually, I lie. Let's go ahead and do an example. I want to do an example. So let's take, for instance, chlorine. What is the effective nuclear charge of a outer p electron? So Z effective for a 3p valence electron. That'd be something that you would see. So our electron configuration here is 1s2, 2s2, 2p6, 3s2, 3p5. So we're looking at one of these electrons. So we would say we have 4 plus 2 outer shell. So we have 6 total electrons that are in the outer shell. Okay. Then we have 8. So 6 plus 2, 8 electrons in n minus 1 shell. And then our other core, we have 2. So we take our 6 times by 0.35 for those outer shell electrons. And it's 6 because this has 5. We minus 1 for the one we are looking at. Then we take our 8 times by 0.85 and add that to our 2 times by 1. So our S in this case would be equal to 10.9, and then we can put that into Z effective is equal to our atomic number. In the case of chlorine, our atomic number is 17, so we take 17 minus 10.9, and that'll give us an effective nuclear charge of 6.1. Okay, now I'm really done. Okay, bye y'all.